Hello everyone, I'm Felix from Georgia Tech. Today I'm going to present our work, ConfuciuX, Autonomous Hardware Resource Assignment for DNN Accelerator using reinforcement learning. Nowadays, there are a lot of exciting DNN applications like object detection, image segmentation, or even playing games. To accelerate those DNN applications, a lot of DNN accelerators are designed. They are featuring high parallelism via thousands of PE, and they use network-on-chip to do data communication. And they maximizing the data reuse via mapping strategy. Here's our outline. We'll introduce motivation first and then come to our problem formulation and introduce our method and go to the evaluation part. The architecture of DNN Accelerator includes two parts, data flow strategy and hardware resources. Data flow strategy includes compute order and parallelism strategy. Hardware resources includes processing element, PE, and the buffer of PE, and it depends on the tile size. So the DNN model will be mapped onto the accelerator, and you will get its performance like latency, energy, power, and area. Now let's look at data flow strategy. The convolution 2D, for example, you can map it like an NVIDIA style which parallelizes across the output and input channel dimension. Or you can map it like a Shidano style which parallelizes across the Y and X axis of the activation dimension. And for this work, we assume the data flow part is fixed, and we explore the hardware resource part. Now let's look at a common deployment scenario of a DNN model. You have a DNN model, and you have some platform. For each platform, you will have different budget and like different constraint, like power area budget, energy latency constraint. And for each kind of platform, you will want to optimize the PE and buffer assignment to it so that the constraint is met and so that you can optimize your latency energy on it. Usually there are two deployment scenarios. First, layer sequential, which map the model layer by layer to the accelerator, which is commonly seen in cloud cases. And second is layer pipeline, which map the entire model to the accelerator, which is commonly seen in the edge cases. However, the layer pipeline scenario makes the problem more complicated because now you are further dividing the PE and buffer resources to each layer. So why is the per layer PE buffer assignment important? What is the impact of hardware resource assignment on performance and energy? Here we are looking at a figure drawing from MobileNet V2. So this is given the same platform budget and given different PE and buffer resources, what is their latency, energy, and area performance? And you can see that different layers react to the PE and buffer very differently. So the research question will be, can we learn to optimize the assignment for each layer to minimize the latency or energy and meeting area and power constraint? And now we are going to the problem formulation. So you have a DNN model, you have some platform constraint like power and area, and you will have an objective to optimize like latency. And you have a deployment scenario like LP and data flow. Then you want to find the per layer PE and buffer assignment, and you will try to fine tune it. And finally, you will have a design that is high speed, low energy, and conform to the constraint. However, in reality, you could have various different kind of model, thousands of different platform constraints, and so on. And each combination of them, you need to find and customize the PE and buffer assignment for it. So this is actually a heavy loading job for the ML practitioner. So in this work, we try to find an auto optimization agent that can do this job for us. Specifically, it is finding the per layer PE and buffer assignment for layer pipeline deployment, which optimize the objective and stay within the constraint. Now let's look at design space. Take a simple example. Let's say you could have a PE and buffer goes from 1 to 128. Then you could have this kind of combination. For a mobile net, you could have 2 to the 728 combinations. So let's say you can do one data point at a second. Then you will need 10 to the 211 years to do it. So the sampling efficiency becomes crucial. We define the sampling efficiency as the performance improvement on the limited number of samples. And second is the discrete reward space. And reward here for us is the performance and energy respond to the PE and buffer assignment. So they are discrete and undifferentiable. So actually, we need a gradient-free method or use some reinforcement learning method. Here we describe some method we can leverage. First is heuristic that you manually design the DNN accelerator hardware resource assignment. Or you can use classic optimization method like GNT optimization, particle swarm optimization, and so on. So they are gradient free, but like they have low sample efficiency. And they are mostly in use for hyperparameter search for neural network control system or EDA tool. And they are reinforcement learning like A2C, PPO2, and so on. And they are reinforced based. And they have higher sampling efficiency than classic optimization method. And they are mostly in use today like robotic, games, and neural architecture search. In this work, we leverage reinforcement learning for the hardware resource assignment problem. Even though we use reinforcement learning, which is known as more sample efficient, but the design space is still large. So we divide the problem into two-stage optimization. The first stage is reinforcement learning-based coarse-grained global search. Specifically, we limit the action of P buffer to 12 different values. We choose P size empirically, as listed in the table. And for the buffer size, we increase by the unit of tile size. It means that when the data flow strategy is fixed, the buffer requirement per PE for a specific tile size is fixed. For example, if an PE is generating one output, it will need 9 weight, 9 activation, and 1 output. So the total buffer size is 19. If a PE is generating 3 output, then it will need 27 weight, 9 input, and 3 output. So the total size is 39. So we choose specific buffer size for various tile size in the PE. By this, we can discrete the combination from 2 to the 728 to 2 to the 104, which is a lot. However, the search space is still large. So for here, we choose to use reinforcement learning to drive the search process. For the second stage, we use genetic algorithm for local fine-tuning. What it does is that it takes the first stage solution and perturb it a little bit and see how the performance change. So the search space is limited and small. So for here, we choose to use light and fast GA-based method. Because of the design space, our algorithm does not promise optimal, but it optimizes the solution with high sample efficiency. Here is the overview of ConfuciuX. It is a two-stage optimization. The first stage is an RL-based coarse-grained global search. Second stage is GA-based local fine-tuning. We'll go to the detail in the next slide. So after some iteration, it will output a coarse-grained solution and go to the next stage. And the detail of it will be described in the following slides. So after some iteration, it will output a fine-tuned hardware resource assignment strategy. So the whole flow is called ConfuciuX. And we will have the 5 input blocks as we described in the previous slides. They will be set up in the environment. So now let's look at how reinforcement learning works. You will have an agent, you will have an environment. An agent will do some action and get the reward from the environment. And then make observation and go to next step and make next action, get the next reward, and make next observation, and so on. Until the environment terminates, an episode terminates, and the agent will update its decision policy. So for us to put into our problem, our agent should be a hardware resource scheduler, and our environment should be the hardware performance estimator. Now let's see how we cast the hardware resource assignment problem to a reinforcement learning process. So the goal is, given a power area budget, we want to find the per layer PE buffer assignment in a layer pipeline deployment scenario, such that the objective is minimized. And the algorithm works like this. For each step, we are treating a single DNN layer. The agent will assign a PE buffer assignment to a layer, and the environment will track the remaining power area budget. For each episode, we are treating an entire DNN model, and we will run multiple steps until the environment terminates. The environment terminates when the entire DNN model is run, or if the environment runs out of area or power. And we will run multiple episodes until the algorithm converges. Now let's look at the detail. You will have an objective, like latency energy, and some constraint, like area and power. And we have an agent whose policy network is an RNN-based network, and we use a reinforced Bayes method to learn it. And our action is number of PE or buffer. And our environment, it includes a hardware cost model. And we use Maestro, which is an open source DNN accelerator analytical model. And the reward is the objective value that we are interested in, like latency and energy. And sometimes you will get a large penalty if the constraint is violated. And observation includes the current DNN layer description and last action, and some status like the number of steps I'm in the environment and whether the environment is terminated or not. Here we show a walkthrough example of our algorithm. The agent will make observation of the current layer, and it will make action. And then it will get the reward from environment and observe the next state. So it will get the current state and get the previous action. and then make the next action and get a reward and so on. And sometimes you will get a penalty because you violate the constraint. And when the episode is terminated, you will calculate the accumulated reward and update the agent. And you will go to the next episode, and the whole process goes on again. And we plot the accumulated reward in this graph across episode. And you can see from episode to episode, the reward goes up, and it will converge to some point, and that's where our algorithm terminated. Now let's look at local fine-tuning. First, now let's look at the action space. The action space is decided by the step size. For example, if you have a step size of 4 and the PE, you have 64 PE currently, so the action space will be from 60 to 68. Now let's look at how it works. You will put the first stage solution into genetic encoding. So essentially, you put those PE buffer value into a series of value, and in GA, we call it genes. And you will make a lot of copy of those genes into a population, and then go to the genetic operator. First, mutation. So in the mutation, you will do some perturbation of the values, and you will get mutated genes, and you will randomly do this to all of the population. And then you will go to crossover. In crossover, you will randomly swap some value in the genes, and then you get crossover gene, and you will do this randomly to all the population. And you will evaluate your population and select some good one to go to the next iteration. After some iteration, your solution will converge, and you will have a fine-grained solution. Now we go to the evaluation part. For evaluation, we compare against multiple classic optimization methods like similarity, annealing, Bayesian optimization, genetic algorithm, and so on. And for IO method, we compare with 6 different IO methods. For the model, we compare under 5 different models like MobileNet, MNASET, and so on. We give them different constraints like power area of like different cloud and IoT constraints. And we optimize across like latency and energy objective. And we use 3 common data flow strategy. And for each of the algorithms, we give them the same sampling budget. It's 5,000 budget. So for the reinforcement learning, it's 5,000 episodes. First, we compare with optimization method. Here you are looking at the graph using different algorithms to optimize the latency of MobileNet V2 under different constraints. And you can see many methods cannot find valid solution because of the immense design space and lack of sampling efficiency. And ConfuciuX can consistently find valid solution with similar or better performance than others. Then we compare with RL-based method. So we compare with 6 of them, and to be precise, the ConfuciuX is reinforcement based. And we also show their search time. First of all reinforcement learning can find valid solution. And ConfuciuX takes about 30 minutes to run it, and it is 4.7 to 24 times faster. ConfuciuX finds similar or better solution with less search time. So now let's look at the impact of local fine-tuning. Here you are looking at a graph of latency converge across episode. Here we show the result of different experiments. Different experiments are like different model and different hardware constraint. So this is the first valid result, and this is the first stage solution, and this is the second stage solution. In average, RL-based global search can optimize the solution by 74%. And in average, GA-based local fine-tuning can further optimize the result by 33%. Here is a sample of solution found by ConfuciuX, and this is on MobileNet V2. You can see that for the depth-wise convolution layer, ConfuciuX actually gave them less resources, and ConfuciuX actually optimized the resource assignment for each layer. In conclusion, for DNN accelerator design, data flow strategy is widely discussed, but how to optimize the hardware resource assignment of it is rather unexplored. The search space of this is extremely large and discrete, so the sample efficiency of the algorithm becomes crucial. At this end, we propose ConfuciuX. It is a 2-stage optimization flow which utilizes reinforcement learning for coarse-grained global search and genetic algorithm for local fine-tuning. ConfuciuX can be treated as an end-to-end black box optimization tool for hardware resource assignment of DNN accelerator, which could potentially reduce the manual tuning effort of ML practitioner. All the code for running ConfuciuX and other baseline optimization methods are available online at this repository. Thank you.